Oh, you can log out before I else concept. Let's check.
Alright, can we start? I'm sure. We can turn that off. Yeah. So, like I mentioned before, the last couple of weeks, there's a project information and team thing that is due this Thursday. And I've been getting a few questions about this. I just want to remind you, all you need to do at this point is to decide what kind of project you want to work on. And it could either be a competitive or an exploratory project. I'm not going to talk about what they are right now. But the important thing that I've mentioned to a few of you in person is, let's say you choose to do an exploratory project because you have some project that you want to actually continue and add some machine learning flavor to. And maybe in a couple of weeks, when you write your project proposal, you discover that it's not going to work out. At that point, there will be a milestone for everyone in a couple of weeks. And at that point, I'll move you to the competitive project. But you need to have a good reason to have selected the exploratory project in the beginning. You can't just say, oh, let me try this now and then move to something else. Another thing is, many of you pointed out, on Canvas, if you select the project type, not project theme, select the project type to be either one of these, you only get 2.5 points out of 5. I don't know how to fix it. So what I'll do is I'll just, or my DAs will change all the 2.5 to 5 eventually, so don't worry. Any questions about projects? So this is due by Thursday, and it should not take more than a couple of minutes of your time. And it's not like this is the end of the conversation. I just want this to be the start of the project conversation. It's not like once you make this decision, everything is frozen and you go around the bar. There's some flexibility. Of course, there's another announcement. There's a homework that's due today. Hope all of you have started. If it's not, there's still time till midnight. There's been a lot of very useful conversation about the homework on the discussion board. Please take a look. Maybe you have a question that's already been answered there. Maybe there have been some hints that that you probably could use. And also, most of the questions were about the experiment part. And speaking of the experiment, there was I hope you saw the announcement on campus about the cross-validation data. It turned out there was some mixture between the split and we just have a new cross-validation split that was uploaded Saturday. And so you can, nothing can change on your part. All you have to do is rerun the code on the new split. If you downloaded the data before Saturday, please download it again and make the minor changes. Any questions about the homework? About either the experiments or the previous parts of it? Yeah?
During cross-validation, is it possible that on, say we just take like 4 of the folds, that a value of a certain attribute would not show up in the folds that we're training on?
Oh, I see. So it is entirely possible, and in fact, it could happen in. Yeah. So let me just try to dig into the question a bit. So the question was, let's say you have the split, and you have trained. You're doing cross-validation, and a certain feature never shows up in the training part of the folds, the 4 folds that you set aside for training. And at test time, you need to do something about that feature. Is that the question?
Yes.
Yeah. So of course, that's entirely possible because we don't need to control the data. So there are really 2, and I'm assuming that the question really is what do you do with that situation?
Yeah.
Right. So there are 2 ways of addressing this. One of them is to use the entire data, all 5 folds, to kind of keep track of what attributes exist. And so, so that at when you're testing on the first fold, there's no surprise. You could do that, but there's a problem with that method. The problem is that the same thing that you described could happen in the future. There could be a feature whose value never shows up. Now, if a feature never shows up during training, it will never be part of the tree. Which means there's no reason to worry about it because it's ignored anyway. So it should not cause any problems, right? So that's one answer. The other answer is any learning algorithm has standard methodologies for addressing missing values of features and missing features and such things. That should be part of the learning anyway, and this should be taken care of by such things. Like for example, if instead of a feature not being present, let's say a certain value of the feature is not present, and it shows up at test time, you should treat that as if it was an unknown value or a missing value, and move on. That could happen. You know, everything that can go wrong with data will go wrong eventually. So your learning algorithm and your prediction process should be prepared for that. Does that give you something to think about? Does this happen though?
It happened to me.
Oh, it happened. Okay.
Okay.
Okay, good. So at least you're not alone. Other questions? Yes?
I got a question. Maybe you just have the wrong answer on that one problem, but you said 3 decimal places on part 4 for whatever it was, special function.
Sure.
In my calculations, it was 0 up to 3 decimal points, and then it started cutting values after that. Can you give us a hint, like maybe what the 3rd decimal point and 1 of them or 2nd?
So I haven't done the calculation myself.
So it could be that far off, and you still haven't solved that problem yet?
Oh, yeah, fine.
That's fine, okay. So
in that case, just give us enough. So here's the thing, okay? I don't care about the 14th decimal place or 4th decimal place. My concern is that you know what you're doing. And so your homework, what you submit should give us enough information to be able to judge whether you know what you're doing. So it's not like there is the grading is going to be done using a script. Believe me, we've tried. So there are humans who are going to be reading the TAs. So there will be some, we will understand if you put a 4th decimal place, or it's not going to keep bring the thing crashing down. More importantly, you need your homework should, the submission should convince us that you know what you're doing, and it's not completely, you did not just pull 4 numbers out of thin air and put them there. And also, on a related note, give us the opportunity to give you points. So show your work. And that will kind of, even if the last answer is wrong, it will give us something to break. Other questions? So, everyone comfortable with the homework? Is everyone done? If you want more of this, there should be another homework coming up maybe tonight or tomorrow. I mean, it does keep you off the streets. We're trying to get it done today or tomorrow, but it's possible that it could show up Thursday. In the next couple of days, there will be homework. And that homework will involve linear classifiers and the mistake-bound model. That homework will involve you implementing the perceptron algorithm, which we'll see maybe in the next lecture, and will have you thinking about what is called the mistake-bound model. Alright, another announcement. There's the Data Science Day, that's this Friday. I've spoken about this before, please show up. There will be some fun talks and a panel discussion with the industry, a bunch of industry people. And if you're looking to meet other people across campus who are thinking about similar things as data, like machine learning or data mining or artificial intelligence in that sense, this would be a good event. Alright, just a quick recap of announcements. There's the project team information that's due Thursday, there's a homework that's due today, and there's a data science day on Friday. Any questions, or we're going to start the lecture? Alright, I guess the homework was too easy, because usually around this time there are a lot of questions. I'll keep that in mind for the future homework. Alright, today we're going to look at linear regression. We're going to continue looking at linear regression. I briefly introduced this in the last lecture, and we'll see what it is and look at gradient-based learning for the first time. Just to quickly recap linear regression, the task is to predict a real valued number, and that's why it's regression. It's linear because we assume that the real valued number we need to predict is a linear function of some input features. Just like with the linear models that we saw, the inputs are vectors, and if the idea of a vector wall is, you think of it as an array of with d elements, and the goal of learning in this case is to produce a linear function that mimics the training set. The training set consists of pairs of instances with labels. In this case, instances are vectors and labels are numbers, and we are going to approximate the function. So we are going to assume that the given an input x1, the label y1 was produced as a linear function, and a linear function is parameterized by a collection of, I said d here and n here, so let's just make them all n. The input is parameterized by, okay, there are multiple bugs in this. The input is parameterized by some set of weights, and together we call them the weight vector. And the goal of learning is to discover a weight vector that gives us that best, in some sense, on the training set. And we've seen this before, so I'm going to quickly go through this. Linear regressors, if you're given a single dimensional input, x1, and the goal is to predict a single number, a linear regressor would look like a line. It's to find the line of best fit across these points, and when a new point comes along, let's say this point here, the prediction is you just find this value here. Just compute the value of that w1 plus w2, x2 and x1. Okay. Similarly, for polynomial, for two-dimensional inputs, you're not finding a line, you're finding a plane. And I want you to understand that this is just a modeling choice. Life may not be generating data using this linear function. It's possible that life is more complicated, but to make your life simpler, you're assuming that the points are generated using a linear function. And if nature behaves differently, by making this modeling choice, you're implicitly willing to live with the error. And this is an important thing that you should be aware of. Anytime you commit to a hypothesis space, it could be decision trees, it could be linear classifiers, in this case it's a linear regression, or it could be a 17-layer neural network. Anytime you commit to a hypothesis class, you are committing to this assumption that nature generates data this way, and if nature truly did not generate data this way, there will be an error and you live with it. And this is, in making a modeling assumption, you are making an assumption about the nature of the problem. So, the goal of learning in linear regression, and this is roughly where I stopped on last Thursday. Are there any questions about this? About linear regression? We didn't cover much of it for you to have questions maybe, so there will be, don't worry. So, just like with all other linear models, the classifier, the regressor, is entirely specified using this collection of weights, the weight vector, and the goal of learning is to discover the best weight vector for any training set, or for the given training set. So, we need to know, so to answer that question, we need to quantify what does best mean. Remember, for decision trees, we had this vague intuition that a best tree is the shortest tree. And we decided, and then until someone came along and proved that finding the shortest tree or the smallest tree is intractable, so we had this greedy heuristic. Now, we need to decide what is the best linear regressor. In order to do that, we will define this notion of error. So, let's say the true label for some example, let's say we have an example xi, yi. And if for this xi here, if the weights were w, imagine that we knew the weights, and let's say the weights were w. If the weights were w, the prediction would have been w transpose xi. It's the dot product between the weights and the features. That would have been the prediction, but now we also know that the ground truth is not that, but the ground truth is this yi here. So this is the prediction by some w, and this is the ground truth. And given that we are dealing with numbers, a natural way of measuring error is the difference between these two things. Or more reasonably, the absolute value of the difference between these things. Because you don't want to overshoot yi by too much, and you don't want to undershoot, if that's the word, yi by too much. You want it to be exactly at yi, so if w transpose xi is equal to yi, like is good, and the error is how far you are away from it. And a natural way of measuring the cost of a mistake is how far you are away. So it's the absolute value of the difference. Now, let's say that we want to find the best weight. We want to find a w that is the best. In other words, imagine absolute values are a little awkward to deal with, so instead we'll just take the square. Right? So the penalty that the weight vector w has to incur for making a prediction on an example xi, yi is the difference between the ground truth and the prediction squared. And the penalty that the weight vector has to deal with on the entire data set is the sum of all the penalties on the entire data set. So, given a weight vector, we can quantify its cost or total penalty by adding up all the penalties on each example. I have half there because we're going to take derivatives and things just become easier, but the half is just a constant. Does this make sense? And this, if you've not seen this before, this could be a slightly weird idea. The function j here is a function that penalizes weight vectors for being not so good on this particular data set. Questions? some point in the class, I like to say that if you have a question, ask it because 30 other people usually do. Yes?
So you're going to take the derivative earlier?
Yep.
Which variable?
With respect to W. We'll get there in a minute.
So I see that we're squaring the difference between these two.
Right?
So that means that large errors are going to weigh more into this cost function than
Yes.
small errors.
Least mean square regression has that problem.
Okay.
Larger errors tend to dominate these things.
So if we had an outlier in our data set, that
Yep.
would really screw up our weight.
That's exactly right. And in fact, if you want to continue that line of thinking, you can generate an artificial data set where all points are perfect except for one outlier and see what happens. I won't tell you the answer. This should be a fun exercise. Okay, so think about questions. This will, if this doesn't bother you, then you are really in good shape. If this bothers you, it doesn't matter because we see this so many times that it will become normalized. So what we have done here is I've defined this function j. You can think of j as the cost for the weight vector w on the entire training set. Today, more often than not, that function is called the loss. It's the loss of having chosen this particular w instead of all other possible w's. So it's the sum of square costs over the entire training set. Now, once you have a way of quantifying, so keep in mind, w corresponds to a regressor. Changing the w changes the regressor. Every w is a different hypothesis. And now, the goal of learning, a natural way to define learning is to say, I would like to find the w that has the least cost on this entire data set, or the least loss. So, by quantifying the error or the loss of any weight vector as a function of the data set, I can now define learning in terms of just minimizing that function. Now, once we have to minimize functions, we know how to minimize functions. That's basically calculus 3 or 2 or I don't know, high school algebra, I'm not sure. I don't know when it shows up. So, the goal of learning is to minimize the total cost or total loss over the entire data, and this is why it's called least mean square regression. So we define the loss to be the mean square. It's actually the total, not the mean square, it's the sum of the squares, but instead of mean, if I just divide by m, the number of examples, this becomes the mean. So I'm defining the loss as the mean square error, and the goal of learning is to minimize the mean square error, and if you minimize the mean square error, you get the least mean square error. Yes?
Yeah, I was just going to ask that. So why are we dividing by 2 instead of m?
Because I'm dividing by 2 because when I take the derivative, the 2 at the top will cancel out. I could have divided by m, but you will see in a minute that that is going to get cancelled out because I'll set this to 0, and it doesn't matter. And it's just a constant, and as Suresh likes to say, what's a constant between friends? So it doesn't, we're going to do this all the time, but if it makes you sleep better at night, we could always say put an m here. And you will see that it goes away. Yes?
Are there restrictions for when this function is convex, or is it always?
This function is convex, and I may not be proving that in class, but if you're familiar with convexity, it's not a terribly hard proof. It turns out this function is convex, and maybe I'll mention this in a bit. Alright, so this is probably, for some of you, this may be the first instance where you see learning being recast as an optimization problem. It's an optimization problem because we are minimizing functions. Learning as optimization is probably the most dominant strategy for learning today. You may have heard of TensorFlow and PyTorch and such things. All these libraries essentially frame learning as optimization, and the game is always about defining a loss function in a certain way. And you can I mean, all of you hopefully have seen the idea of minimizing and maximizing functions. And the standard way of minimizing a function is to take the derivative of the thing and set it to 0. And if life is particularly friendly to us, setting it to 0 will give us a system of equations that are easy to solve. It turns out in the least mean square regression, that is in fact true. So you can actually on paper calculate the minimum value of this this optimization problem, and that's going to be an exercise for you for later. But for now, I'm not going to do that. You can actually solve this analytically on paper, but I will not do that. Instead, I'm going to take the hard way out just to introduce the idea of learning as gradient descent. How many people have seen or heard of gradient descent? How many people know gradient descent? A subset. It better be a subset, right? So, those of you who have not seen gradient descent, this might be the first time you are seeing this idea, and it's a natural idea. And let's see what gradient descent is. It's a general strategy for minimizing functions, and it's got it traces its history back to I don't know when, but suppose you're given some function like this, j, and I can plot the function, and this is not how it looks, but w is a vector, but I'm pretending that w is a number here. So this is w, and the vertical axis is the function, and the curve shows the value of w at each point. So gradient descent makes the following. It's an algorithm that looks like this. You start off with some initial guess for the minimum. The goal is to find the minimum. So it's to minimize some function that looks like this. You start off with an initial guess of w. It could be this point that I've highlighted there, and that point may or may not be the minimum. What do we know about the minimum? We do know that at the minimum, it doesn't matter how we got there, at the minimum, the gradient is 0. Right? The first derivative of a function at the minimum is equal to 0. And we can compute the gradient. There's another nice intuitive interpretation of the gradient. At any point, the gradient gives you the direction in which the function grows the fastest. So, some people like to think of this as we live in Salt Lake City, so it's useful to think of analogies that involve mountains. Think of it as a rather silly way of getting to the bottom of a mountain. You're standing somewhere on the slope, and you need to get to the absolute minimum. Wherever you are on the slope, you look around locally and you find which direction is the mountain going up the fastest. That's the direction of the gradient. A natural thing to do is to go in the exact opposite direction. Right? Does that make sense? I mean, it may not be the soundest thing to do in the mountains, but maybe it kind of works. So what you do is the gradient gives you the direction of the steepest increase, and the goal of gradient descent is to go in the exact opposite direction. In this case, in this picture here, there are only two directions for w. Either w can go that way or that way. And the gradient, what I've drawn there, the line that I've drawn there is really the tangent. The gradient points in this direction, and so we need to reduce w. So w goes, you take a step in the opposite direction to the gradient, and you go to w1. And again, you compute the gradient. The gradient gives you the direction of the steepest increase. You take a step in the opposite direction. You keep doing this till you come to some point that you are convinced has a gradient so small that it doesn't matter, and you don't need to take any more steps. So, more formally, what you do is in gradient descent, you start off with an initial guess for the weight vector. Keep in mind, w is a vector. It's some direction. Vectors are essentially directions. So you start off with some initial guess for w, and there is choosing the initial point may or may not matter depending on the kind of function we are dealing with, and you keep iterating until convergence. And convergence is just another way of saying until you're happy. and until you're convinced that you've got to close enough to the bottom. And you essentially keep repeating 2 steps. First, you compute the gradient of the function at that point. So at this point, we computed the gradient here. At this point, we compute this gradient. You compute the gradient of the function at that point, which is just the first derivative at that point. And then you take a step in the opposite direction to the gradient, and you go back to the you repeat this process. You keep going down until you get close to the minimum, or till you get to convergence. Questions before we instantiate this idea for these things squared? You and then you. Yes.
How do you know how far to step back?
How do you know how far to step back? That's one of those black arts. Like those of you who read Harry Potter, this is like a dark art. So let's say you're here, and you take a gigantic step, and you go here, and you have actually put yourself in a position that's worse. So there are heuristics for this, and certain kinds of the step size policies have certain guarantees. In general, the idea is you don't take a very large step. We will quantify this more formally, but you don't take a very large step, and as you have taken more and more steps, your steps become smaller. So the step size keeps decreasing as the number of iterations grows. So that, because the intuition is that as you have been running this procedure for a long enough time, you're close to the bottom of this curve, and so you don't want to take very large steps, otherwise you might overshoot. Yeah?
How do you handle the case when there's more than one minimum? So local minimum.
Yes.
Identify the global minimum?
No, that's a $1 million question. So if you notice, I have a function here that has only one minimum. But of course, nothing prevents a function that looks like this. And what happens is, we don't know. There are no guarantees. Gradient descent is guaranteed to get to the bottom of the function if the function has exactly one, where the local minimum is the global minimum. In other words, when the function is convex. In all other cases, gradient descent comes with no guarantees. It may come with guarantees in some more special cases, but the general guarantee is if you have a convex function, this will work. If you don't have a convex function, good luck. In fact, if you don't have a convex function, your initialization point becomes important. Yes?
Yeah, but isn't the solution usually just to run the algorithm 10 times for
And
the dissociation point?
That seems to be the current popular strategy. 10 years ago, machine learning researchers would not touch a function that looks like this. Something changed. Something changed in the mentality of research around 2010, and I know exactly what changed. We started getting better results by ignoring this assumption that convexity is a sacred thing. But we don't have guarantees. And the idea, as you said, is you start off with multiple initialization points. You start here and you go down the hill. You start here, you go down the hill, you start here. And you try to find the lowest point. There was another hand that shot up and went down. Okay.
So if the curve is like flipped, so I don't have the maximum, so will it like find the maximum?
Yes. So if your curve looks like this, then you do gradient ascent. Then you go in the direction of the steepest. You go in the direction of the gradient rather than in the opposite direction of the gradient. And so this is useful for maximizing function.
Oh, so it will not find like way down at the very left.
So what will happen is if you do gradient descent on a function of this kind, and let's say this function goes all the way down to negative infinity, gradient descent will keep going down. So if you try to minimize a function that goes to negative infinity, you are in for a world of pain. But on the other hand, if you have a function of this kind, maybe you're trying to maximize it. We will, when we get to logistic regression, we will see how we care about maximizing a function, but because we have all this software for minimizing things, we'll just put a minus sign in the front and minimize the function. But that's a good intuition. Everything that I said only works for functions that look like minimizing convex functions that look like balls. Other questions? Alright, let's instantiate this thing for the least mean square objective. So I said this works for any function. Let's instantiate this for the function that we just invented for least mean square regression. It's this is just a slightly more formal version of the same idea. You initialize some W naught, pick randomly, and then you compute the gradient. So yeah, you compute the gradient of this function of J. Let's call that this symbol here, the term at the front is the nabla, so I'm going to call this nabla J. And then, so first thing to keep in mind is this quantity is a vector. The gradient of a vector, a function, so if J is a function that maps an n-dimensional vector to a real number. It can, because W is an n-dimensional vector, it maps a collection of numbers, all of them are treated as a vector, to a single number, which is the loss or the loss. The gradient of a vector function from vectors is itself a vector. So the thing in the box is a vector, and then what we do is once we compute the gradient, we update our estimate of W. We had a WT, now we're going to get to WT plus 1, and the way we do that is to take a step in the opposite direction of the gradient. Opposite becomes minus, so minus the gradient, and R is the learning rate or the step size, and as the question came up, the step size becomes an important deal, but for now let's just pretend it's a small constant so that we don't overshoot. So, are we done? Can you implement this? Okay, let's say the step size is a small constant, it is 0.001. I'm just making it up, but what else is missing? Yeah? Oh, okay, you need a, okay, let's see what are the things that are needed. So we need a stopping condition, and we'll discuss that in a minute, but there's something more pressing. We need the gradient. I pretended that the step 1 is easy. Let's see whether it actually is. So we need to compute the gradient of this function with respect to W. It turns out for this particular value, this particular definition of J, the gradient is actually easy. We'll get to functions eventually when the gradient becomes problematic, but for now it's actually easy. And probably the only time in this class I'm going to actually compute the gradient of a function and show you all the gory details. Eventually I'll start kind of hand waving furiously. But for now, keep in mind the gradient of the function is itself a vector. So see, now my dimensionality is D. So the